Physics, part 226. In real situations, however, frictional and other resistive forces can cause the oscillator's energy to be dissipated, and this energy is converted eventually into the heat energy. The oscillations are said to be damped. The total energy of the oscillator decreases with time. The damping is said to be light when the amplitude of the oscillations decreases gradually with time. This is illustrated in the figure. The decrease in the amplitude is in fact exponential with time. The period of oscillation is slightly greater than that of the corresponding free oscillations. Heavy damping causes the oscillations to die away more quickly if the damping is increased further. Then the system reaches critical damping point. Here the displacement decreases to zero in the shortest time without any oscillation. Any further increase in damping produces over-damping. The displacement decreases to zero in a longer time than for the critical damping. Damping is often useful in oscillating systems. For example, vehicles have springs between the wheels and the frames to give smoother and more comfortable ride. If there was no damping, a vehicle would move up and down for some time after hitting a hump in the road. Dampers, shock absorbers, are connected in parallel with the spring so that the suspension has critical damping and comes to rest in shortest time possible. Dampers often work through hydraulic actions. When the spring is compressed, a piston connected with the vehicle frame forces oil through a small hole in the piston so that the energy of the oscillation is dissipated as heat energy in the oil. Many swing doors have a damping mechanism fitted to them. The purpose of a damper is so that the open door, when released, does not overshoot the closed position with the possibility of injuring someone. Approaching the door, most door dampers operate in the overdamped mode. Forced oscillations and resonance. When a vibrating body undergoes the free undamped oscillations, it vibrates at its natural frequency. We have already met the idea of a natural frequency in chapter 8 when talking about the stationary waves on strings. The natural frequency of such a system is frequency of that first mode of vibration. That is fundamental frequency. A practical example is guitar string plucked at its center, which oscillates at a particular frequency which depends on the speed of the progressive waves on the string and the length of the string. The speed of the progressive waves on the string depends on the mass per unit length of the string and the tension in the string. Vibrating objects may have periodic forces acting on them. These periodic forces will make the object vibrate at the frequency of the applied force rather than natural frequency of the system. The object is then said to be undergoing forced vibration. The figure illustrates operators which may be used to demonstrate the forced vibrations of a mass on a helical spring. The vibrator provides the forcing driving frequency. As the frequency of the vibrator is gradually increased from zero to the mass begins to oscillate, at first the amplitude of the oscillation is small, but it increases with increasing frequency. When driving frequency equals the natural frequency of oscillation of the mass spring system, the amplitude of the oscillation reaches the maximum. A frequency at which this occurs is called the resonant frequency, and resonance is said to occur if the driving frequency is increased further. The amplitude of the oscillation of the mass decreases. The variation with the driving frequency of the amplitude f of the frequency F and the amplitude A of the vibration.